Salam, peace be upon you. My name is
Yeah.
Muhammad Layak Sadipi, the father of Holophase, part 39.5. Resource bound conformance when computation limits certification. We began with one simple insight: pattern comes first. Phi is the permission for distinction, and only lawful relations become public. Identity is what survives transformation. Persistence is continuity through change. Interaction is mutual constraint. And measurement leaves traces that memory stabilizes. Models compress those traces. Prediction narrows futures. Learning updates structure, and intervention steers outcomes. Computation then appeared as rule governed pattern transformation. Now we reach the next honesty. Not every real pattern is publicly certifiable whenever we want. Legibility itself is constrained by time, memory, energy, sample size, and computational reach. When we arrive at computation, many people feel that we have entered a new kingdom. They imagine that the physical world is one thing and the digital world is another. On one side are rivers, mountains, bodies, storms, trees, stars. On the other side are software, models, algorithms, data centers, machine intelligence, and simulations. It sounds as if computation belongs to a second reality, hovering above the first. But we have disciplined ourselves too carefully to allow that split. Computation is not a ghost world. It is pattern transformation within reality. And once we accept that, we must accept something equally important. Computational limits are also real. They are not bookkeeping details. They are not minor annoyances. They shape what becomes publicly readable and what remains hidden behind the fog of insufficient resources. This is the core of Part 39.5. A pattern may exist, it may be lawful, it may even be identifiable in principle, yet it may remain uncertifiable in practice because the resources required to render it publicly legible are beyond what is currently available. Time may be too short, memory may be too small, energy may be too costly, samples may be too sparse, noise may be too high. The required search may be too vast. The computation may be lawful and still the certification may fail. So we install a new honesty. Resource status must be part of certification structure. This sounds technical, but it is actually very human. Imagine a child trying to finish a 1,000-piece puzzle on a tiny table in a dim room just before bedtime. The image on the box exists. The final arrangement is real in possibility. The rules of fitting pieces are clear. Yet the child cannot certify the complete picture under those conditions. There is not enough light, not enough space, not enough time, and not enough working memory to hold the partial structure together. The picture is not unreal. It is simply not fully legible within the available resources. That is the spirit of this part. The same truth appears at every scale. A doctor may suspect a faint pattern in a scan, yet not certify it without better imaging or larger comparison sets. A climate scientist may know that a more exact simulation exists in principle, yet not have the computational power to run it at the needed resolution. A mathematician may know that a proof procedure is valid, yet also know that carrying it out for a large class of cases would take longer than a civilization can wait. A telescope may point toward a distant world whose signal is present, but too weak to separate cleanly from noise. In every case, reality does not disappear. Public legibility simply fails to fully mature under current conditions. This is why resource limits are not merely engineering inconvenience, they are scientific constraints. They shape the boundary between what can be asserted, what can be bounded, what can be explored, and what must still be refused. We therefore need a clean way to speak about computational outputs. Not every answer produced by a procedure has the same certification status. Some outputs are exact, some are bounded, Some are heuristic. Unless we distinguish this clearly, confusion enters immediately. An exact result is one that is fully determined relative to the declared encoding, domain, and lawful procedure. Within the relevant framework, the output is not guessed, it is completed. If we count 7 apples in a bowl under stable conditions and clear visibility, 7 is exact relative to that task. If we add declared numbers under declared arithmetic and obtain a determinate sum, the result may be exact. Exactness does not mean cosmic perfection. It means that within the declared domain, the procedure reaches completion without material approximation changing the outcome class. A bounded result is different. Here, we do not claim the single exact answer, but we do certify a lawful range, tolerance, interval, or confidence structure. We might say the journey across the city will take between 20 and 30 minutes under present traffic conditions. We might say the temperature tomorrow will likely fall within a declared range. We might say a measured quantity is this value plus or minus a stated tolerance. A bounded claim is not weak. Often, it is the strongest, honest claim available. In many real settings, bounded certainty is more mature than false exactness. A heuristic result is different again. A heuristic is a useful strategy for finding plausible answers under constraint without supplying full exactness or a fully certified bound. A cook seasoning by feel is using a heuristic. A chess player pruning unlikely moves is using a heuristic. A doctor making an initial triage judgment from pattern familiarity is using a heuristic. A search engine ranking pages is using heuristics. A machine learning system flagging likely anomalies is often heuristic in exactly this sense. Heuristics can be powerful. They can save immense time. They can guide inquiry toward what matters. But by themselves, they do not equal full certification. This distinction is one of the great protections of this part. Modern culture is full of polished outputs that look more authoritative than they really are. A number appears on a screen with decimal precision, and people assume truth has arrived. A model gives a score, and people treat it as judgment. A simulation renders an elegant image, and viewers start speaking as though the world itself has been exhausted. But appearance is not certification. A heuristic can be helpful and still remain a heuristic. A bounded estimate can be valuable without pretending to be exact. A lawful science must make these differences explicit. Think of a farmer looking at the sky and saying, "Rain will come by evening." That may be a heuristic grounded in long experience. It may often work. A weather model running declared equations over measured atmospheric data may produce a bounded forecast with known uncertainty. That is different. An exact prediction of the state of every air molecule across the atmosphere would be a very different thing again, and for practical purposes, it is unavailable. The point is not to humiliate heuristics. The point is to keep them in their lawful place. Heuristics aid inquiry. Bounded methods support disciplined public claims. Exact methods support stronger claims where available. Confusing them deforms trust. This is where conformance enters. A computationally mediated claim must not only have a procedure behind it, it must also declare the resource and output status under which it was produced. That declaration is what we call resource-bound conformance. It says, here is what kind of result we have, here is what it cost to obtain, here is where approximation entered, here is how memory, time, sample size, and energy shaped the answer, here is where the method may fail, and here is what would be required for others to reproduce or challenge the claim. Without this, a result floats free of its own history. and a result without history is not yet public knowledge. It is an orphaned conclusion. Provenance, therefore, matters deeply here. If we say a model discovered a pattern, we must ask from what data, through what preprocessing, with what exclusions, through what search pathway, under what runtime limits, using which approximation choices, and with what stopped conditions. Did the algorithm run to completion or stop because memory ran out? Were outliers removed? Were only successful runs reported? Did randomness enter the search? Were many seeds attempted and only the best shown? These are not fuzzy details. They are part of the meaning of the claim itself. To see why, imagine a loaf of bread brought to a table. It smells wonderful. Its crust is beautiful. But if we are told it proves a new baking method, we need to know more than that the loaf exists. What flour was used? What hydration? What rise time? What temperature? Was sugar added? Was the dough repaired midway? Did 3 failed loaves come before this one? A single attractive outcome without provenance cannot support a strong public claim. Scientific computation is no different. Stochasticity sharpens this further. Many computational procedures involve randomness, sampling, or noise-sensitive variation. A search may begin from random seeds. A simulation may estimate through repeated sampling. A learning system may converge differently across runs. A medical statistic may shift depending on who happened to be sampled. A poll may swing because the sample was small or skewed. Once stochasticity enters, the certification status of the output depends not only on the rule, but also on repeated behavior, uncertainty structure, and sample dependence. A lucky run is not yet a public truth. Imagine fishing in a lake. If we lower a net once and catch one strange fish, we may have found something remarkable, or we may simply have found an outlier. If we lower the net many times under declared conditions and observe stable patterns, our claim becomes stronger. Sample size matters, variability matters, repetition matters. When stochasticity shapes the path, resource honesty must include how many draws, how much variance, what convergence checks, and what confidence or failure behavior accompany the result. This is why we install 4 gates. The first is the resource gate. A computationally mediated claim must declare the practical limits relevant to its production and reproduction. Time cost, memory demands, energy or infrastructure burden, where material, sample availability, precision needs, and major cost barriers must be visible. Two results that sound identical may have very different certification meaning if one was produced on a common laptop in seconds, while the other required a rare supercomputer, proprietary preprocessing, and weeks of runtime. Both may matter, but they are not the same public object. The second is the exact, bounded, or heuristic gate. Every output must declare its type. Is the answer exact within the stated domain? Is it bounded with explicit uncertainty? Or is it heuristic, useful for search and suggestion, but not yet carrying the full burden of certification? Without this gate, semantic inflation begins. Rough outputs start dressing like judgments. Suggestions start pretending to be verdicts. The third is the approximation gate. Approximations are often necessary and entirely lawful, but they must be named. Where was the problem simplified, sampled, compressed, linearized, discretized, rounded, or truncated? What was lost? What is believed to remain stable? Under what conditions does the approximation stop being safe? A flat map is useful, but it distorts the globe. A sketch may capture a face, yet lose forensic detail. A simulation grid may reveal large-scale flow, while missing fine structure. Approximation is not the enemy. Hidden approximation is. The fourth is the failure mode gate. No claim is mature unless it declares where it may break. A vision system may fail in low light. A medical classifier may fail on underrepresented groups. A weather model may widen uncertainty after a certain horizon. A language system may fail in rare or adversarial cases. A bridge design may hold under tested loads but not beyond them. Public trust grows not only from knowing when a system works, but from knowing when it does not. These gates give us firewalls against three common smuggling operations. First, hidden heuristics. If a system is using pattern-guided guesswork without full certified bounds, it must not speak as though it has delivered final judgment. Second, practical impossibility disguised as exactness. If an exact solution exists only on paper because carrying it out would take unlivable time or impossible memory, then exactness in principle must not masquerade as exactness in present certification. Third, omitted resource dependence. If the result depends materially on exceptional infrastructure, dataset size, special hardware, or narrowly available conditions, that dependence must not disappear from the public claim. This point is more profound than it first appears. Resource-bound conformance teaches us that existence is not the same as legibility, and legibility is not the same as certification. A pattern may be there, yet unread. It may be partly read, yet only heuristically. It may be narrowed, yet only within bounds. It may be certified exactly only in small domains and not in large ones. Science matures when it learns to say which of these situations it is actually in. Think of an ancient library after a flood. Some scrolls remain intact and can be read exactly. Some are damaged, so their contents can only be reconstructed within bounds. Some fragments merely suggest themes through heuristic comparison with other texts. The library contains knowledge, but different parts of that knowledge occupy different certification states. A mature scholar does not collapse those states into one tone of certainty. Resource-bound conformance asks science to show the same maturity. Or think of the night sky. Some stars are plainly visible. Some distant bodies are inferred through bounded signals. Some faint fluctuations are only candidate hints awaiting more telescope time, better instruments, and stronger statistical support. The universe is full of structure, but structure is not uniformly legible. The same is true inside a cell, inside a market, inside a brain, inside an ecosystem, inside a city, inside a court of law, inside an archive, and inside a machine learning pipeline. Legibility is uneven because the cost of reading is uneven. We can express the heart of this part in a very simple form. Certification power is not only a function of whether a pattern exists. It is also a function of whether available resources are sufficient to render that pattern publicly legible. In plain language, we can say certifiability equals pattern accessibility under declared resource limits. We do not need to treat this as a mystical formula. It is a reminder. If access collapses, certification collapses, even when reality remains. Another way to say it is this: result status equals output type plus resource declaration plus provenance plus failure disclosure. When any of these are missing, trust should weaken. The equation is not there to intimidate. It is there to compress the lesson into a form that can travel. A supermarket gives us a small but powerful example. Suppose we walk in with a shopping list and want the cheapest complete basket. In principle, there is one exact best basket and they're all combinations of brands, discounts, sizes, and substitutions. But to search every possible basket might take absurd time. So we use a bounded method or a heuristic. We compare likely options, accept a near best basket, and move on. Nothing shameful has happened. The shame only appears if we then announce that we found the provably exact cheapest basket while hiding that we merely used a fast rule of thumb. The marketplace teaches the same honesty as a laboratory. Now, shrink down to the scale of molecules. A protein can fold into complex shapes. In principle, the space of all possible folding pathways is enormous. Scientists use clever approximations, energetic bounds, learned priors, and heuristic searches to reach useful structural predictions. These achievements are extraordinary, but their certification status depends on what was actually done. Was the structure directly measured? Was it inferred within declared confidence? Was it generated by a model trained on known structures? Was the search exhaustive or guided? At the molecular scale, resource-bound conformance protects us from praising the map as though it were already the territory. Now expand to the scale of society. A court may receive millions of documents in a major case. No human team can read every line instantly. Search tools, ranking systems, and summarizers may help surface relevant material. That is lawful and often necessary. But if the court begins treating ranked relevance as certified truth, danger enters. A heuristic retrieval system can support inquiry, it cannot silently become the judgment itself. The same principle applies to policing, hiring, lending, welfare administration, and education. Resource pressure often invites shortcut systems. Shortcut systems may be helpful, yet where certification affects lives, hidden heuristics become morally serious failures. This matters everywhere. We should also notice that more resources do not automatically mean more truth. Bigger models, bigger datasets, faster chips, longer runtimes, and larger memory can expand legibility, but they can also amplify hidden bias, brittle approximation, and false confidence if discipline does not keep pace. A giant telescope still needs calibration. A giant dataset still needs provenance. A giant simulation still needs declared approximations. A giant neural system still needs failure mode disclosure. Resource abundance without epistemic honesty can create more impressive illusions rather than better public knowledge. There is a beautiful humility in this. Resource-bound conformance reminds us that science is not the art of sounding certain. It is the art of proportioning claims to the lawful reach of evidence, computation, and declared method. A small but exact result may be stronger than a grand but hidden heuristic. A bounded answer with open error bars may be wiser than a sharp number with secret approximations. A refused claim may protect truth better than a celebrated overclaim. In this sense, refusal is not the enemy of knowledge. It is one of knowledge's immune systems. So, when we stand before any computational result, we should learn to ask a new sequence of plain questions. What kind of answer is this? Exact, bounded, or heuristic? What resources made it possible? What approximations entered? How much data supported it? Where can it fail? What would another honest group need in order to reproduce or challenge it? These questions do not slow science down in the bad sense. They slow down overclaiming. They make progress sturdier, They turn black box awe into public structure. That is the deep human meaning of this part. We do not dishonor reality by admitting our limits. We honor reality by refusing to pretend that our present windows are larger than they are. We honor science by making the cost of seeing part of what is seen. We honor public trust by marking the difference between a clue, a bound, and a completed certification. And we honor the future by leaving behind claims that others can inspect, refine, correct, or surpass, rather than only admire. From the child's puzzle to the flooded library, from the weather map to the courtroom archive, from proteins to galaxies, the same law now stands before us. Patterns may outrun present legibility. Computation may lawfully transform structure without yet delivering full certification. Resources are not outside knowledge. They shape the public form knowledge can take. Once that is understood, information itself can finally be described with more clarity. Information will no longer look like a mysterious substance hidden inside matter. It will begin to look like structure constraint disclosed through lawful differences, readable only within windows that resources can sustain. This also gives us a discipline of speech. Often, the hardest scientific virtue is not discovery but restraint. Institutions reward confidence. Audiences want clean answers. Markets and politics often prefer sharp outputs to honest bounds. But lawful public knowledge sometimes requires saying less than desire would like. We may say the pattern is suggestive, not certified. We may say the estimate is bounded, not exact. We may say the system flags candidates heuristically and must not be treated as final judgment. These are not weak statements. They are strong forms of epistemic honesty. So, what do we refuse? We refuse claims that hide heuristic status. We refuse claims where approximation materially shapes the outcome but remains undeclared. We refuse claims that ignore resource infeasibility while speaking as though exact certification has already been achieved. We refuse claims that conceal sample weakness, broken provenance, or known failure modes. We refuse outputs that ask for faith where public structure has not yet been lawfully established. By the end of this part, several things are installed. First, resource honesty becomes part of certification law. Second, the exact, bounded, and heuristic taxonomy becomes mandatory for computational outputs. Third, computational conformance requirements become visible. What it takes to reproduce, test, challenge, or trust a claim is no longer hidden in the background. Fourth, the public learns that a powerful tool is not the same thing as an omniscient oracle. Computation remains within pattern reality, and its limits remain within epistemic reality. This prepares the path to the next part. Once we understand computation as rule-governed pattern transformation, and once we understand that certification depends on resource-bounded conformance, we are finally ready to speak clearly about information. Not as a ghostly substance drifting through matter, not as a magical fluid poured into reality from somewhere else, but a structure that constrains what patterns can happen, what transformations remain possible, what futures stay open, and what differences can still be made legible. That is why Part 39.5 matters so much. It teaches us that the world may be richer than what we can presently certify, and that honesty about this gap is not weakness. It is the only path by which public knowledge can remain trustworthy while reaching toward realities larger than our current powers of reading. Always peace be upon you.